Yeah, good afternoon, students. So, in the previous class room discussion, we had a discussion on the different instruction executions in five-stage hardware. Now, today we are going to discuss about these control signals, so which are required for the control unit while it is executing these different types of instructions. So, now I would like to share my screen. So, here control signals. So the lecture objectives of this today's session. So this session will develop students' knowledge on signals which are needed to control the operation of the different components in the processor. So now the meaning of what is a control signal. So the control signal, the operation of the processor hardware component are governed by the control signals. So these signals will determine which multiplexer input is to be selected, what operation to be performed by the ALU, and so on. Since data are transferred from one stage to the next in every clock cycle, so we are using these interstage registers, so which are to be enabled when that particular during that particular stage when the clock pulse is generated. So the interstage registers what we have used is RA, RB, RZ, RY, RM and PC temp. These are the different interstage registers which we have used here. So the contents of other registers, namely the program counter and the IR and the registers files must not be changed in every clock cycle. So the role of multiplexers is to select the data to be operated on in any given stage. Okay. So that is the reason we require these control signals at every stage of the instruction execution. The hardware components are governed by or controlled by these different types of control signals. Fine. So, what are the different control signals which are used for data path? Okay. So, during this data path, so the register file has three 5-bit address inputs allowing access to 32 general purpose registers because 2 power 5. So 5-bit address input is there. So there are 2 power 5 means there are 32 general purpose registers you can address that. So two of these inputs are address A and address B, which determines which registers are to be read. Okay, they are connected to the fields in the IR register. So this is IR 27 to 31 bit position and IR 22 to 26 bit position in the instruction register. So the third address input, that is address C, selects the destination register into which the input data at port C are to be written. Fine. So this is also be at in the IR register. Okay, destination register which we are using here, that is 17 to 21 bit position we are using that. Fine. So here if you see that the what are the control signals which are related to this data path. So this is what the data path diagram you have seen that. So now this register A, which is a 5-bit A value is used here. So that is 27 to 31 IR register content. So this is address B 26 to 22 to 26. Okay, so 5 bits are used for selecting of this address A and B. So these are control signals. And another one is the RF underscore write. This is whatever this is what we are calling it as, it is a control signal here. So the multiplexer mux C select the source of that address. So we have assumed that three register instructions use the bits IR21, 17 to 21, and other instructions use IR22 to 26 to specify the destination register. The third input of the multiplexer is the address of the link register used in subroutine linkage instructions. Okay, subroutine linkage instructions. Okay, so new data are loaded into the selected register only when the control signal RF underscore write is asserted or it is enabled. Fine. So the multiplexers are controlled by the signals that select which input data appear at the multiplexer's output. So that is the address C. You see that there is a control signal C underscore select will be there. So among these 0, 1, 2, so which signal has to be selected, which will be acting as an output of mux C as an address C. Fine. So this is what we are calling it as. For example, when B underscore select is equal to 0, mux B will select. For example, B underscore select is equal to 0. This is another control signal. So B underscore select is equal to 0 means that uh, mux B selects the contents of register RB to be available at the input INB of the ALU. Fine. So again, this is ALU underscore op is also another control signal, okay, which is related to, given to this arithmetic logic unit, and these are the different condition signals are there based on that arithmetic operation, whether it is going to generate as sign bit is enabled like that, it will be there. So the operation performed by the ALU is determined by a k-bit control code, that is ALU underscore op, which can specify up to 2 power k distinct operations such as such as addition, add, subtract, and or XOR, etc. Totally 2 power k distinct operations we can select. So when an instruction calls for two values to be compared, a comparator performs the comparison specified. So the comparator also generates condition signals that indicates that result of the comparison. So these signals are examined by the control circuitry during the execution of the conditional branch instructions to determine whether the branch condition is true or false. So this is how the data path control signals are there. Okay, so this is the reflection spot for this. Name the different control signals used in the data path. Okay, so what are the control signals used in the data path? So we have the RF underscore write is one control signal, C underscore select is another control signal, B underscore select is another control signal, ALU underscore op is also another control signal, and then this is wise underscore select is also another control signal, and these conditional signals which are related to this arithmetic operation. After carrying out that arithmetic operation, it will choose the condition whether they are the outcome of the condition comparison conditions when we are using the branch instructions. Okay, then the second category of control signals which are required when we are making use of this processor memory interface and the IR instruction register. So the interface between the processor and the memory and the control signals associated with the instruction register are presented in the below diagram. Okay, so two signals which are related to this memory or mem underscore read and mem underscore write are used to initiate a memory read and memory write operations. So when the requested operation has been completed, the interface asserts the MFC signal. Okay, so the instruction register has a control signal, call it as IR underscore enable, which enables a new instruction to be loaded into the register. So during a fetch step, it must be activated only after the MFC signal is asserted. Okay, this is a memory fetch control signal, MFC stands for. So we have assumed that the immediate block handles three possible formats for the immediate value. So this immediate value can be specified either of these three formats as a 16-bit a signed extended value we can specify, or a zero extended 16-bit value, or a 20-bit value that is handled in a special way. So hence its control signal extend also comprises of these two bits, whether what type of immediate value we have used. Okay, so these are the control signals related to this processor memory interface and IR. So this is IR enable is one control signal, extend is another control signal associated with the immediate operand, and this is a mem read and mem write, and then this is a MFC control signal. So this is a MA a control selector is a control signal. So these are the different control signals associated with the processor memory interface and as well as this IR register. The third category of control signals where it is required is that it is required these control signals for instruction address generator. So the control signals for instruction address generator, the signals that control the operation of the instruction address generator are shown in this particular diagram. So this is PC underscore select is one control signal, and then INC underscore select is another control signal. So which select the value to be added to the PC, whether we have to add the word length value 4 bytes to the PC, or whether we have to add this branch offset value which is specified as the immediate value. So it INC underscore select signal will add either the constant 4 or the branch offset specified in the instruction. Then another important control signal is PC select. So it will select either the updated address or the contents of the register RA. RA content we have to take, or updated address, which is the output of this adder, has to be selected. And this another one is PC enable. This is also another control signal. So this is enabled when this PC value is loaded with the RA register contents, so that when it is stored in the PC underscore temp register, so which is nothing but the return address when we are using this subroutine calls, will be used here. So now this is the lecture level practice problem. So you have to analyze the different control signals associated with the instruction generator, data path, and as well as memory processor interface and IR registers. So the lecture outcomes is that you, after completion of this today's session, you will be able to analyze the various control signals used in data path, instruction generator, processor, memory interface, and instruction register. Okay. So thank you, students. Thank you, one and all.